All right. Hi, everyone. Thank you for coming. My name is Rami Krispin, and I'm going to talk today about forecasting, specifically about forecasting at scale. I'm excited for being here and especially talking about forecasting. So a little bit about myself. I'm a data science and engineering manager at Apple. Full disclosure, my talk today is not related to my work. I'm focusing on forecasting and MLOps. I'm open source contributor, mainly in the language of R, also some Python stuff, creating application for time series and data packages. Last but not least, I'm an author of a book about time series. It's very old. Now I'm working on a new book, actually two books, one on time series, the other one on MLOps side, about Docker for data science. And you can find me in LinkedIn, and I have a Telegram blog channel if you are there, so feel free to join. All right, so agenda for today. We're going to talk about forecasting, plenty of it. So we start by talking about explaining the old forecasting process to understand why it's not scalable. And from there we go to general architect of forecasting method in scale. We will talk in more details about backtesting, but the main thing I want to talk about is how to generate features at scale with cluster analysis. So, first thing first, definition. So I'm not sure how many people here have experience with forecasting, so I thought start with some definition. What is forecasting? You cannot explain what is forecasting before you're talking about what is time series. So time series, it's a vector with observation that depend on time. So for each observation, there will be timestamp. And within this, there are two types of time series. First one is regular time series, which means it's equally spaced. The data was captured by interval of time, constant interval, so every minute, every hour, every day, and so on. And the second type is irregular time series, which is not necessarily captured in equally spaced intervals. And essentially, the regular time series is a special case of irregular. And now we can talk about what is forecasting. So it's a prediction of observation that there is a time dimension involved. Okay, so that's the difference between, for example, classification. Classification is also a type of prediction. Here there is a time dimension. And generally, when we talk about time series, and specifically in this presentation, it's referred to regular time series. Irregular time series is a completely different field, which I don't have much of experience with. So generally, in time series, we refer to regular time series, and also in forecasting. All right, now we can talk about traditional approach for forecasting. So typically in the past, most of us, if you're doing in this business for many years, you would have a bunch of time series to forecast, and you would enter like a limit number of observations. The reason that in the past, the methods to capture data were limited, and as we progress with the technology, we have more, everything is digital, right? From our phones, computer, we are capturing logs all the time. We are capturing more data than we can process. But in the past, there was not enough way to capture data. And typically, when you went and analyzed data, you start with defining some business problem. And for example, let's say that you are working in an energy company and you try to understand your business problem is like you are maintaining some infrastructure related to this energy. In this case, it's the natural demand for natural gas in the US. And if you are maintaining the infrastructure for planning capacity, you want to know what will be the demand in the future. So then you go get the data. Without it, you cannot do much. And you start to analyze it. And the reason you analyze it, you're trying to understand what data you have. There are a couple of items you want to check, right? You're not missing data, the quality of data. But then like you also, before modeling, you're trying to get what is the characteristic of the time series, and it will help you in the next step of the modeling. So typically it will involve of some visualization. In this case, we are doing some decomposition of the data. We're trying to identify the seasonality pattern, the trend. You can see here, it's called STL decomposition. We're breaking it down to trend, seasonality, and the reminder is what is not expressed by the seasonal and the trend components. And we also love to check correlation. Time series typically come with a lot of correlation. This is the autocorrelation function, and helps us to identify a lot of the patterns and the models in time series are based on correlation. And the simple way to explain it, if you think about temperature, the temperature an hour ago is very correlated to the temperature now, right? Unless there is some extreme weather, the change won't be as significant. So it's a nice driver for prediction. And then you apply what you learn based on the learning from the analyze step, and you define modeling strategy, feature engineering. You may train multiple models, split the data into some training and testing, score the models. You will run some feedback. You want to make sure that if there is still room for optimization, you might check the residuals. And based on this, if you're happy, you got to the place that you don't see much of improvement, you will generate your forecast. So that's a very long process, and we're just talking about single time series. What if you have two time series, right? So you'll do the same, right? You do for each one the same, more or less the same process. And if you have 200 time series, right? You see where I'm going, right? It will be, and for those who saw yesterday my talk, so that's the only Will Ferrell give, I promise. But it's not scalable, right? And today, most of the people doing forecasting, they're working with many, many time series on the hundreds or the thousands, and that's a challenge. So now we can start talking about forecasting at scale. And let's define, and this is my definition, not textbook. My definition of what is forecasting at scale is whenever the level of effort of adding additional series is nonlinear and decay, right? So most of the time you spend time on the building the infrastructure, the first time series, but then adding additional will be in a lower cost. So that's the important definition. Second one is the modeling approaches that we are using. It could be that you may define different strategy for different data sets. Compute, right, infrastructure, if you want really to scale and you have like a limitation of a timeline and stuff like this, you want to make sure that you have enough GPUs, right? Last but not least, you need to acknowledge there is a trade-off and scaling that you might have a potential drop in your accuracy. That's given. There are ways to handle it, but you're not giving the same love like when you're dedicating for one series and then you're trying to work with hundreds. It's not the same kind of like attention, right? So going to be some trade-off. All right, so let's start with the general architecture of this process. I won't go into details because of time, but I just cover a little bit the main items. Then we talk about backtesting and feature engineering. So the first thing, you want to get the data. You want to transform your data. You want to make sure you normalize it and it's ready to use. And it's a very easy functionality. And once you have the data ready, you start I call it backtesting orchestration. I'm not sure if, some of the terms like I wasn't sure what is like the textbook, because there's not much textbook about deploying time series at scale. But essentially, the backtesting orchestration is the brain. And it's more like data management. There is no modeling in it. It's taking all the pieces, right? It's taking the features, the recipes, there is a setting, and orchestrate the whole process. So that's the brain. But essentially, if I need to define what is backtesting in a nutshell, is the time series equivalent for cross-validation in machine learning. And so it's a technique to train time series. This is a screenshot I took from Uber engineering blog. They have great articles about backtesting. And if you're familiar with cross-validation, the idea is the same, right? You split your data into multiple training and testing partitions. You train your data on each training partition. You fit a model, and then you predict the observation on the testing partition, and you score the model performance. And you repeat it for all the partitions, and the idea is very simple. You want to evaluate the performance of the model with data the model didn't see on the training, and give you some indication how well the model will perform on the actual forecast. There are two types of backtesting, or the main two types. The expanding window, which you start with some, you start from the beginning of the time series, and each time when you're moving the sliding window for your testing partition, you extend and you use all the data available up to the point. And there is the other popular method, which is sliding. You keep always your training set at the same size. Typically, if you have a lot of changes in your data, you would use this method. Otherwise, I prefer to use the expanding window. And with this also there is horse racing. And horse racing, as it sounds, you are throwing a bunch of models, and you are doing a race between those models, and you choose the one that performs best. So it's and the combination of the two of those, when you're running backtesting with horse racing, I feel like it's very equivalent to autoML. Like the idea, the concept is the same. Typically, time series, the terminology is different, but the concept is the same. So here is an example, visual example of horse racing with backtesting. You see here, this is I think also it's a natural gas in the US. I took it from a package I created many years ago. So I'm not sure what is the time series, but it looks like a very cyclic data, so it's probably natural gas. And the color, there are 6 partitions here, and the lines are representing different models. So I'm using 2 flavors of Rami here, 2 flavors of ETS, old winter, and regression. And I'm just running a test between, a race between those models. I'm finishing the training. I collect the results. I'm scoring the results. So I have a leaderboard, and I use this leaderboard based on some success criteria that you define. You select the one that performs best, right? So the straightforward, very similar to machine learning. So that's backtesting, very useful to scale, right? You can, if you want to do AutoML, you drop it on your data. If you know your characteristics of your data and you know what work more or less, you will let some models to run, and for each series to fit the best model. It's also with like any automation, there is a double sword kind of that you need to be careful that with automation, sometimes things can seems really good on your testing, and then in reality they work less. So obviously, it's good to visualize and see. One thing to mention about this graph is like there are 2 types of, what we want to see is models that are, this is the distribution of the error. We want to see consistency. So this really nice consistency, but the error rate is high. So we prefer to see something like this, but lower. We want to choose the model with a lower error rate. So going back, that's backtesting. The backtesting, typically you will have some setting file, define your recipe for the backtesting. How many partitions, what the size of the partition, how many resources you want to allocate, CPU, or anything that you want to control. And then there are the recipes. So this is where you define the type of modelings you want to use for each series, and the features. And I think that this is like where, so far, it all can be automated. This is where we spend most of our time to understand what features we need. And this is the, I believe, most costly in terms of time when you try to scale, to understand the features. And I'm going to talk about this in the next slides. You can package your, so that's the modeling. You can package it inside, like, let's say you're using R or Python. You can just build functions and send your data, but it's nicer to work with APIs. And the reason that it removed the language, if you want to use multiple languages, it's removed this barrier that you need to navigate between different languages. I'm mainly using R. They are a great resource for forecasting, but sometimes there is some models that might be available only in Python. So when you use this approach, you can mask it and let the API handle the language. You just send the data, you get, with some settings, you get output. Once you get the outputs, you score the results and push the results to some database. And again, like there are more to it, right? There is a monitoring layer, and you can have a dashboard that support. You can visualize the result. You want to identify where stuff are not working. You want to do some post-mortem, but in simple, this is like a very simplistic way to think about it. So now let's talk about this part, the features and the recipes. How do you, when you have many time series, how do you understand? And the main challenge is when working at scale, is how to identify the right model or the models you want to use, and what are the features you want to bake into this process. Maybe I pause for a second and explain what are features. So you can categorize forecasting models into two types. The one that work out of the box, like Arima, that you cannot use regressor. So they look at the past. There is some regressor on the back end, but you cannot influence the results in terms of like external regressors. So if you have a series like the natural gas that is like very cyclic, it will work. They are lucky. I'm not working with such a type of data. Typically, you will get data that were, COVID impact, structural break, and a lot of stuff changing. And this is where you want features, because you want to make sure the model understands what happened. So you need to give. It's like when you're doing prompting engineering. When you're giving a context, the LLM will work better. So the same idea. So here is one method to understand the features. I got into it a few years ago when I saw this article by Professor Rob Hinman. For those who are not familiar, he's one of the main contributors for forecasting in the world. He's based in Australia, and he's writing a lot and doing a lot of research about forecasting. They came with this idea that you can how to analyze multiple time series. And the idea is very simple. So let's say that you have a bunch of time series. You take each time series and you calculate a bunch of features. And what you're doing by this, you are collapsing each time series to a row. And let's say you care about trends, seasonality, and correlation, and so on. So you start to calculate those matrices for each time series, and you get a table with features. Essentially here, each row represents a specific series, and each column represents a specific feature. So the first one is trend, the second one is spike, and so on. So there are about 25 features. Once you have those features, you want to do some dimension reduction, and we're going to do some clustering. So first thing is you want to look at the data with 2 or 3 dimensions. So in this case, I'm using PCA, principal component, but it's not limited for PCA. You can use other methods that might work as well. And then you want to cluster. You want to start to look at the patterns and see how the patterns reflect in the data. And there is more than one way to look at it. And the idea here, you see, we got some clusters. Probably there is some similarity. What we can do after is to understand what is this similarity. We can look at each cluster, take a specific series, a representative of this cluster, do the process of analyzing it, understand the features, get some model, or with backtesting, a framework for modeling, and then apply it for the rest. You capture the error rate. If it's reasonable, great, you can scale. If not, there is like a feedback process. Maybe you need to select other series and repeat the process. But that will save you time. So here we have 250 series. You can focus on 5 series and apply it on the rest. You might have to do some adjustment, but in terms of scaling, you don't need to do it for each of those 250 series. And once we get, that's how when you look at the cluster, visualization is really helpful. You can look at the features, understand, in this case, we had the 4 clusters and see what are the unique characteristics of each cluster. So you see over there, the green one has a high linear trend. The linearity is all over for the green cluster, but the correlation is very high, right? Which is different from the second cluster or the third. So it's unsupervised learning. It's more, I feel like for those who, I'm more in my life focused on the supervised learning. It's nice because it's not deterministic, but you get the results, you can measure the error. In unsupervised learning, it's there are more than one options. There is no right or wrong, and it's more art or sometimes it's more art than science. So we can run a short demo. Let's see how we're doing with time. I spoke with someone last week. I was in a meetup, and she told me that the presenter with experience never do live demo, and she's right. I'm taking the risk because I think it's worth to see it, and I hope it won't break. I built like a app on the way over here, on the flight, just to demonstrate this and explain what the app is doing. Still working. Okay. So let's go quickly about this app. So the app, and I will figure out, I found it. So the app has a very simple, I think I skipped a slide to explain what we're doing. All right, so what we're going to do now, we're going to take a 250 series representing different consumption of natural gas in the US, coming from 5 categories. The data is monthly, and each category will have a series from each state. So we have approximately 50 series for each category, and that's why we have 250. This is one of the categories, and you see it's very, very cyclic, nice, but not all of them look like this, and now we can look at this. So essentially on the back end, what is happening? Loading the data, calculating the features, calculating clusters. So it's pre-calculated. Now we can review the data and start to explore. Now what you see, the data in 2 dimensions. There is PC2, the y-axis, PC1 is the x-axis. We also can go to 3 dimension. Okay, and now we are looking, so there's two views over here. So we can do it by variable. We start with variable, we can look it by the cluster. So let's start at the variable. Now we are looking at the area, meaning the state. Doesn't really, it's very colorful, it's nice. 3D always, plots looks nice, but not really meaningful. So let's maybe look at different variables. So we can start with the process, right, the category. So what we can see here that definitely we have here a cluster. So this category is vehicle fuel consumption. And if I click on it, you can see the series. And you see it's a very step. But then like the rest here is all over. We can see there are different, but the nice thing is like, you can identify that this, you can do a distinguish between the category, this specific category and the rest. But we want to maybe find something, more insightful. So we can start look at the trend. And the trend feature is scaling between 0 and 1. What does it mean? That 0, there is no trend, and 1, there is trend. So you can a little bit rotate it and see how it's look, and you can already see, like, if you're looking only in trend, there is nice clustering, they are close together, and probably it's a big influence about the way it's structured like this. And you can see those are the ones that with lower trend. So we can understand, for example, for the series on this area, we want to use a model. We see there is a nice seasonality. This specifically coming from Colorado, but there is no trend. So we don't need to worry about structural break and other stuff that you would look at different series. And we can move on and look at, let's do spike. No spikes. It's very, all look the same. Okay, we have here, okay, we found spike, right? So it's really amazing how does it work that it gives you like this information. So you don't need really to look all over. It will tell you like those 3 series, they have problem. You need to build features for those. You can automate it, right? You can run if you really want to take it to the next level, you can calculate all those KPIs and set a threshold. And the way I would approach it is apply some model, calculate the residuals, and see where my residuals are higher. And this is where I'm going to set a feature to flag this anomaly. And under assumption it's anomaly, right? In other cases, you need to be very careful, because if it's, let's say, a recurring event that is not seasonal, for example, Easter occurring every different date. So you may have it's repeated, but it won't be on the same date, so you won't capture it as a seasonal event, as opposed to Christmas. So I think you get the gist, like, of using the, looking at, we can also look at correlation. Again, you see it's very organized really well. You have series with high correlation, series with somewhere in the middle, and series with almost no correlation. Last but not least, let's go over cluster. So now this view, you get, I calculate the cluster and I'm projecting it back to the PCA. And again, you see like it's a nice separation. And I have somewhere between 2 to 5. So let's start with 4 clusters, right? It makes sense to look at 4 cluster. And I think this is where we can start work on identify the models and the features, right? So I just plot those 4. It's not a limit to this. Again, I didn't have much time to spend on it on the flight. But the idea is like you need now to identify what is special on each cluster, what features we want to add, and based on this, you can go to the modeling. One more thing that's it's very nice here that it's also identify outliers. There is a reason this is far away. Okay, let me, right, that's a really, let me remove the cluster view and then we can, so if you go to those one, this is like a 0 and then there is a step, right? This is probably, you want to drop it. There's no like much to do over here. But it's also, you can identify series that are, something is wrong with them, they are not really insightful or useful. All right, so in conclusion, scaling depend on infrastructure, right? You want to have some cloud base if you need it, right? You don't want to run it on your laptop, and the type of models. Back testing is a great method. If you want to start, that's where I would start. There is a trade-off between going also to the feature. So if you don't have the time to go and identify the features, back testing would really a good place to start. Feature engineering is important. I cannot emphasize how important. The difference between good model and excellent model is typically the type of features. And this method that came from Professor Wildman is amazing. I think it was when I saw it actually. I took a workshop a couple of years in one of the conferences that I attend, and he presented. It was like really mind-blowing. If you I understood like what it really fit to my day-to-day problem. So I highly recommend to go and explore. I have some resource here that you can use. There is the blog post from Rob Einman. There is a seminar paper that's worth using. The code that I use to create this app is available on this repo. I need to commit some stuff, so give me a day. It's a little bit messy. I need to clean it, but it's there. You can go and generate it, run it. I'm using R, but technically you can do it with any other language. And also there is Uber blog post about backtesting. It's really nice explanation. Hey, I will pause here for questions if there are. Yeah.
Thank you for the presentation. Very interesting. I'm just maybe a little bit confused about the process. Is it that you first you have to look at it,
Right.
normalize it, and then you extract features by breaking it up into a friend or tribe and so
Yes.
on, and then you're like, I gotta use all of them because that's not good. If I want good models.
Mm-hmm.
Instead of looking at each individual time series, you want to shortcut it by grouping them into 4 or 5 clusters, and then for each cluster, you
Yes.
specialize which feature to take, and then you apply it to the whole group. Is what I'm having to do when you
Yes.
got it.
Yes.
Instead of having 250, you kind of want to have 5 clusters that you have to kind of do. Then you do the back testing.
Yeah, and then once you figure out, so if you go back to um, okay, so essentially when you start this process is after you did the analysis. So that's what I showed. That's like the analysis, and you feed the features after you do the analysis, and then stream. And the idea is very similar to the concept in computer vision of transfer learning. It's not the same, but like the idea is the same. You learn from one and apply it for the rest. You can still have a room because essentially you check the one of the series over there. You will run some 5 different models, and you see the performance. And even they're going to be one model. For other series, it might be like the one that was good for one might not be for others. So it leave you the room of be more flexible. Under the understanding that they are similar, but there is a limit of the similarity, right? So it gives you more room. Yes, yes.
But like, I guess I'm missing where is the loop because I guess you're evaluating it and then you're kind of looping and
So yeah, so that's like how it will look in production. So after this process, this is like you deploy it in Kubernetes, and yes, it's after you are already, you know, you're happy with your with yes, you are settled in about what you want to use. Um, there is something I didn't include here, but there is a post-mortem right monitoring that you want to see if you have a drift in the performance, and maybe you need to do readjustment. Um, but essentially, that's after. To get to this process, like that's a time consuming, so that's like, you know, what you would use. But then like that's like where you, I should explain it better. When you deploy it in production, that's the
Do you do back testing in production as well? Or you still do back testing?
yes, because I think about like you have a new, whenever you get a new data point, you do refit. Um, you know, over time, if you have the same time series and it's like not really changing, you can then, if you want to serve on compute, maybe look backward and see what are the top 3 models. One of the signs that your system is stable or your modeling is stable, if you always get like the top 3 models are more or less the same, and you can then prune the models, and you know, to save compute time. Yes.
You suggested the retrain every day, right? Because the relational tools, they're so slow. You should every single day retrain with that thing as well. But maybe it doesn't matter that much if you repeat something compared to everyone else.
I think it really, so the question was if you need to retrain the model. So there is a, depending on the type of models you're using, there is tuning and refitting. The difference is that tuning is like when you have models that you need to identify what is the right, um, you know, parameters. Like if you're using some XGBoost, so it's a heavy, like the heavy compute in models like XGBoost is to identify the tuning parameters. The refitting is fairly cheaper. So once you 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 tune your model, you use this every time. But every time you get a new data points, you just do calibration for your coefficient, um, and then like again, like you monitor whenever you see drift. This is where you need to do retuning. Did I answer your question? Ah, yeah.
Do you suggest having one model per time series or trying to maybe use one regression model with all time model?
That's a discussion I had with a colleague. Uh, I think that, you know, now there is some approach of yes, like let's put all of them together, and you just, you know, add like some segment. I didn't try it. That's something worth checking. Um, I think as we go to do more deep learning, as this is where I see. Typically, I'm not using deep learning because I feel like it's expensive and not really going back to, you know, where sometimes the simple method will be better than the complex. But deep learning can handle when you feed multiple series and give you multiple output. That's something interesting to check. I didn't check it, but that's another thing to worth checking. So the short answer, yes, it exists. I know it exists. I never tried. Yes. Yeah. I think you should use, you know, there are many ways, many methods. I think you should use the one that you feel comfortable with the output. I use PCA because I'm not. So in my career, I started with machine learning and did like some clustering, but then I converted to statistic and forecasting, and since then I was mainly focusing on this, and then later MLOps. But so I felt more comfortable to use PCA because I used in the past, but it should not be limited to this. Like if there is a method that might work better, and I think because it's unsupervised, is important that you feel comfortable that you understand the output. So yes, so with PCA you can, yeah, 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 you can, and also with the, I mean, you can go as deep as you can really go deep in clustering, right? You can on the clustering, you can find like there are different methods to find the optimal number of clusters. Um, on PCA, you can use some visualization to understand which one give you the best, which PCA give you the best coverage and so on. I think for the purpose of like understanding direction, like it's very simple, and at least in this case, if you have like more complex, maybe you need to go a little bit complex with this. But yeah, it's that I feel like PCA, it's or dimension reduction, it's a field by itself. Yeah, I my go-to is PCA. Yeah. Well, it's very simple, and compute, and yeah. Any other questions? Yes. Yeah. Yeah. Collect metadata. All the process, like collect the, whenever you're getting realization of data, typically, um, you start to forecast let's say you are forecasting every week, and you're focusing, let's say, until the end of the year. So every week you generate a new forecast. So in parallel, you have multiple forecasts in different stages that are running. Um, and you want to capture for each one, whenever you're getting, that's another pipeline, whenever the raw data is get refreshed, it's calculate on the existing forecast with the realization of the data, the performance, and you want to set some threshold and flag, have some system that flag you, oh, I see, oh, on this specific geo, a change in the trend, I see a drift, that, the data scientist or whoever maintaining it will go and check it. I think, you get some of it, where is it? There's something fun on the other. We're missing something. The nice thing about backtesting that it's calculate the average error rate, right, on different partitions, and it's give you indication. And that's my method to kind of like put a threshold. So, for example, if this model on the model I selected on the testing partitions was on average 4.8%, I can say I want to maybe a standard or do some deviation if in the performance, in the real performance, it's diverging. Send me alert. Yeah. So that should be kind of like your where to start with, how to threshold your model's performance. Okay. there are no other questions. Thank you so much.
Thank you.